Okay, good morning. Good morning, everyone. Nice to see you. Um, okay, last time we stopped about at the electric field and maybe do a little bit of review and um, then actually I will do today also a small wrap up of what we have done this far. And since we are not such a big group, it is also good if you like to ask questions also, then don't feel shy about interrupting anytime. So last time we have seen what happens if you have some charge and what how the force field actually looks like. So we take a major charge here, what you see at the Q plus, and then we have decided we shift around this small test charge. So the idea of the test charge is always that this is actually pretty much negligible. And when we look at of course, you have to think the test charge itself also is cause for some force field. But because it's very minor, the force field will be dominated by this large Q here in the center. And so when we look at the force vector, then this is all determined, of course, also by the small charge, but in terms of um, um, as long as you have the single one, actually it does not make too much difference, but we will have then other ways scenarios. And when we move this test charge, then we always go about that the test charge is actually not dominating the field. But you see, you have a force vector that is pointing in a radial direction from where the major charge is, and it is decaying in its magnitude as we move the test charge further away. And then the idea was, okay, we say there's an electric field. Um, and in this concept, we take the force vector and, so to say, normalize it. We take out this test charge, this small q. And so the electric field is actually something that provides a measure for the force to be expected once you bring in the test charge. And now, I think I had to correct that because actually what is negative here is not the test charge. I have to fix that on the slide. But now you have two opposing types of charges, and now they attract each other. So you see the force vector is pulling into the center, and also as the charges moves away, you see that you get an increasingly smaller vector. So how do we visualize that we were also looking at that time? So now we have an electric field that is also pointing inwards to this negative charge. So we have the definition of the electric field, that is the force divided by the charge. And in the circumstance where we have an electric field generated by a multitude of point charges, then you sum up the force contributions and divide it also each by Q. And you see the formula looks very similar to the formula where we had F for the combined setup of many charges, but also this factor Q is missing. And then we have the unit of the electric force field, and you know force is Newton, you know the charge is Coulomb, so you divide here the Newton by Coulomb, expanded by Newton meter, so Newton force by meter, we all know that corresponds to some work. So that is equivalent to watts per second. So we convert the Newton times meter in watts times second, and then we divide it by ampere second per meter. You see, we can normalize it. We get to the volt per meter. And now there are two ways of visualize this. We can use the field lines, or we can use plotting in the individual vectors. So we have seen that the field line is actually the tangents of the vectors. They follow the tangents of the vector at each individual point. And so you have seen that. Okay, and this actually I asked you last time to give you guess how to plot those field lines. Anybody has some suggestion? Sorry? How do you mean upwards and inwards? So here it's in outward. Okay. And here all inwards. Okay. That's correct. So now, of course, what happens if you have these two charges together, then these field line will start to bend. Exactly, yeah. So you will get then from plus to minus, and these here will then, this one that goes out here will more or less come back down here, so they will bend. And this will look a bit different if you have same in both directions. So here you see this is a different concept. One, you have the vectors here. Each point in this vector field, you can mark and plot here a vector into it. So at that respective location, that is where the vector originates, and it goes into the direction where how the vector is specified, and it has a length that is to the magnitude. And if you look at the field lines, the concept, then it always follows the tangential. So it is continuously going through, so you don't have the individual vectors, but you have one line. But different from the other concept here, you show the magnitude by shrinking vectors. Here, this shrinking is embedded in the fact that the lines get more widely separated. By the way, have you seen I have uploaded a few notes further on Excite? And there's also a small section with questions, which I would like you to look at, that we can do then tomorrow. So that would be actually, there's one section that is homework. Have you seen for tomorrow? So I would like you to go there through it. There are some questions about the things that we have covered this far and partially also do today, and that we can then discuss tomorrow in the tutorial. Also, there's a formula for the mathematics that we will need for the coordinate transformations when we look in cylindrical and spherical coordinates. So just want to bring that to your attention, and you have also updated the slides. If you have something missing, I think not, but then please let me know. So this is the second scenario inwards. And yeah, as you now have the two close to each other, then you get the lines connecting here. And if you have a scenario like that, well, then you will have, we will see that in actually a few moments. This is the scenario that you have when you have a capacitor where you have two charged plates. Then also your lines go from plus to minus. And what you end up is getting here a homogeneous field. Interesting, it also becomes what happens outside of these plates, and that we'll see in a moment. Oh, yeah, by the way, I have here the attendance sheet, and I would like to pass it around. If you please sign it. So what happens here, because now we have two positive charges, what happens to the force vector that goes out here? Any suggestions? Hmm? It repels, yeah. But how will the force line look? The field line, it will go up. Yeah. So they cannot. They repel each other. So the field lines of these will bend down here, up and down. Basically, I'm not sure whether I can do it with the mouse nicely here, but the idea is you have actually both positive charges. Yeah, if you have both positive charges, then what happens is originally we said they go all out in all directions. But if here is a second charge, then this here, you will have a bending of these field lines, because in the end, they repel. And if you bring in here another charge, it will be equally, depends on what. If you bring here another test charge, a positive one, it will repel by this one and this one. And it actually might, in the ideal case, not actually encounter any force acting on it, but it would be a very unstable situation. In the end, it will get out of its unstable position and will be pushed out in one or the other direction. And if you have now the plate, the two plates, then you have a lot of positive charges here, and you have the negative charges here. Then you have just the field lines going this way. What happens here? Well, they also bend a little bit, but these become here very weak, so they will be separated at a very large distance. And in the end, you will have hardly any field behind. So that is a capacitor, but also that you can compute with this formula that gives you this multitude of charges. So there are some ways of visualizing the electrical fields. So there are ways that you can also test yourself. It is supposed to work with semolina seeds that you put into an electric field. So you need some kind of grain or something that has some kind of dipole, some electric dipole in itself, so that it kind of will exhibit an orientation. And I can show you here a video also how these electric field lines can be visualized. This is, however, not with semolina seeds, but that is with some kind of crystals that are placed into some liquid, and there is a um, some electrodes placed into this liquid, and you have some high voltage, and then these small crystals, they align with the, so this is actually some video you can find online also. So you add these, sprinkle here these crystals in there, and they start to also align themselves, so respectively distribute a little bit in this liquid. And then you can actually very nicely visualize this electric field, because the electric field has this interesting property. I mean, in the end, like, I guess many fields, also like gravitational field, it is quite intangible. You cannot really sense it, except for when you bring in some charge, and then it starts to show its effect. And you see here now, you distribute here these crystals, and these field lines are not, of course, it's a visualization of field lines. These are not exactly the field lines, and that's also why they're not perfect. You see, however, that these crystals align themselves along where you also see the crystals, where you see the field lines. There are different experiments that being here executed. So again, there's this crystal being spread, and then you have to wait a bit till that really happens to take effect. And you see they're also not continuous, but where they show up, they are aligned with the electric field. So here you see pictures. Again, the positive charge outward, and here you see the lines of equipotential, and that we will also get into more today. You see here the arrangement of these crystals, and you see they are not perfectly like the lines. You have some things that an electric field line would never do. What do you think that looks strange about it? So for example, you have things here like this looks like it's branching out, or you have crossings. That is not what will happen to a field line. That is shows you that this is not a perfect visualization of the field line, but it is quite impressive nevertheless. Now these are these single charges, plus and negative, and what happens if you bring in the two charges of opposite, then you see they run here from Q plus to Q minus, straight here at that, and then here they go curved out, and here they go straight into the other direction. So you can solve these actually when you later come to Poisson equation, you can solve that. And this is how you expect the field lines, and also again with a visualization based on these crystals that have been sprinkled in this liquid in presence of these plates, these charge plates. And you see in here, in this volume, you actually get really an homogeneous electric field. That means the field is here not varying. It is all oriented from plus to minus, but is of uniform strength from here to here, and it is also not varying here in from bottom to top. But outside here, it becomes inhomogeneous. You get here these curved lines, and here it becomes actually very weak. And also, we will look into that. Um, we'll get into some formulation that will show you why this is vanishing when we are looking at the Gauss law. So homogeneous electric field lines, what is the hallmark of those? The hallmark is that they are all here have the same magnitude and the same direction, independent of the position. And in any visualization of the plot, that means if they have, here you have it with vectors, that means they have the same length, they have the same direction. If you have it in the field line concept, that means you have equidistant spacing here, and that would be your indication for a homogeneous uh, electric field. So, as you see below here, this is schematically represented by parallel and equidistant field lines. So actually, in that point, you can see this drawing here. You could see that as depending, you have to know whether it represents the field lines or the vector concept on such a small snap. It could be either actually. And now it becomes more interesting if you have a multitude of charges and you have these positive or negative charges, you get quite intricate patterns here, how the field lines run. And if you want to solve that, then yeah, you probably want to rely on some numerical solver for the Poisson equation. So, but what you see here now is this is obviously not homogeneous anymore. You see here that the field lines actually get a variation in the spacing here. They're quite wide, they get narrow here, and they're also curved, so they are neither in direction uniform nor in their strengths. And that's a typical sign of having, or that is what we call an inhomogeneous field. You see, however, that you have also regions, like for example, here or here. So locally, you actually can say that you have some kind of homogeneity. So, or well, depends on, it's not perfect homogeneous, but it's close to homogeneous. If you go in certain local areas, you can say locally you have a homogeneity. And that's actually in the end also what you have with such a parallel plate capacitor here. You have inside a homogeneous field, outside not so much, but it doesn't really matter because the field is pretty much all concentrated inside. So we can, usually we will talk about it as a homogeneous field, but you have to see always where you draw your boundary for that. Okay, let's do some wrap up on what we have seen this far. So what are special features of the electric charge? We have said the electric charge, um, when we look at well, actually the charge itself also, the force field that we here have in this Coulomb law that we observed is, it cannot be seen, but the impact can be observed. That's a special case here for the electric charge. Now, where do I? So it cannot be seen, but it can be, but its impact can be observed. Then we have summarized that the fundamental property of elementary particles, that they are fundamental property of elementary particles, the electric charge, and that it is also the source of the electric, or respectively also electromagnetic interaction. So then we also said there are two types of charges. So there's a plus and a negative charge. And also, very important, there's only a pairwise generation in a closed system of these charges. So if you generate only negative or plus charges, then obviously you're not in a closed system. The charge is quantized, and we denote it with U or small e. What is the charge? Is about 1.6 times 10 to the minus 19 coulomb. So these 1.6 you certainly shouldn't know by heart. Times 10 to the minus 19. You can give it more specific, but I think usually in many cases with the 1.6 times 10 to the minus 19, you're quite fine off, at least for an initial guess. This is the elementary charge of one electron. What other properties does the charge have? It actually has a range of action. And that range we have seen is described by the Coulomb law. What happened? Jiggle the mouse here a bit. So it has a range of action, and also the charges are the source of the electric field. We know it has a range of action. We also know that like charges repel each other and dislike charges attract each other. So the one thing, like that they have this range of action and the fact that they attract or repel each other, that basically is summarized in Coulomb's law for point charges, and that you might know by heart already or not. If not, then you should know it by heart. So the charge, the force on charge 2 due to charge 1 is opposing the force on charge 1 due to charge 2. So they are always of opposing sign. They are 1 over 4 pi epsilon naught, and they are proportional to the charge Q1 and Q2, and they are proportional to, they're pointed in the direction of the distance vector, and they are decaying with the square of the distance vector. So we have said, we write that here 1 over the absolute value cubed, and here R2 minus R1. So that means this gives us here, the last term gives us the direction, and that the decay is given in the denominator. And that is for a single charge. And then we have actually the superposition principle, which applies if you have a multitude of charges. Also, that is a very important takeaway from the previous or from the lecture this far. We have the super, and then what is the formula for that? That basically is summarizing the contribution of each individual charge onto that respective charge Q. So this is the force on charge Q is Q over 4 pi epsilon naught, and the sum of each other charge's contribution that runs from I1 to N, and that is Q sub I times R minus R sub I to the power of 3 here, the absolute value, and R minus Ri. So this is also the equation 1.2, and this up there is 1.1. So this follows from the fact that the range of action, I mean, it's not following from that, but this we have said the range of action and like charges repel each other. This relates these statements to these equations. Then we have also said now that the charges are the source of the electric field, and that actually yields for us the definition here. This is defined electric field as so. Also, this is a very important formula to take along, and that yields you then also the extension for a system of n point charges, which all have q sub I charge and are located at r sub I. Then your electric field is a superposition. It's given here as this. You can pull out of the summation 1 over 4 pi epsilon naught, and you sum up here I is equal to 1, runs from 1 to n over q sub I. Okay, thank you. Now it's already vanishing again. Also, this formula you need to know by heart. That's equation 1.3. E is a vector field, and by definition, E is also a force field. We see it simply because it originates from this formula, right? And F is a force field, so E, in conclusion, is also a force field. Okay, this is a wrap up of, I think, some of the most important aspects that we have covered this far. Many more to come. But now I would like to actually, because we are looking at some integration again, I would like to proceed and do also a little bit of math recap concerning integration along curves and passes. And then that is what we need now to, in the subsequent section, we will look at the work that you perform when you shift some particles, some charged particles through that force field. And then the question is, when you shift it, then you shift it along a certain line, a path, a curve, whatever you call it. And for this purpose, we will need to do some integration along curves, and that's why I would like to go here and look at that for a moment. Okay, the problem we're going to encounter is the mechanical work. And work is always something where you calculate basically a work for an arbitrary path. And this is within some force field. So there are various force fields we know in physics. And well, it could be also, for example, the gravitational force. If you carry some object up on the hill, then you will also exert some force onto it and you will change its potential energy. And also, if you are moving the charge through the electric field, you do something similar. So we have, you may call it the curve path or a line integral in a vector field. And we have then an integration of some vectorial quantity, this force quantity, along that given path. And that will yield us the work, the electric work or the mechanical work, for example. So what are we doing when you're calculating such a path or curve integral? Basically, you follow the curve along that specified, you specify the curve and then you follow that curve within that force field, and you sum up the contribution of that force field at every point of this curve, and you add them all up. So we have a bit of, yeah. Oh, it's gone again. Oh, thank you for pointing it out. Is it back? No, there is some bugging here. Sorry, this. Okay, I'll fix that later. But there's 3 steps to the solution of the problem. And I will show you that here in this math recap. And then actually these exact same 3 steps I will show you then later when we actually apply it to the electric force. So first step is you have some kind of curve in this force field. So you have an arbitrary force field, you specify a curve along that. And the first aspect is that you actually parameterize this curve and you find a suitable way for parameterizing that. I mean, this is an important aspect if you are trying to do this in a analytic fashion. If you are doing it numerical, then you of course has more options. So the second step is then you parameterize the vector field. So first you do the curve, then you parameterize the vector field accordingly. And there you insert the parameterization of the first step of the curve. And then in the end, the third step here is you adapt the differential line element inside the integral to parameterize. And I want to give you an example here now. And the example looks as follows. So you have here a graph where we have the force field, and I plot that here with these red arrows. And this is an arbitrary force field now. See, I have, this is not a homogeneous force field, as you see. They're becoming here longer as far as you go from, for larger, or as far as you go from the x point is equal to 0 away. But it could be an arbitrary force field now. So there's our y component. And so the force field is here denoted here with a small f. F is our force field, it's a vector quantity, and is a quantity of a radial vector. And in our specific case, this is equal to minus f naught. So that is f0 that, or f naught, that is a constant. And it is only directed in x direction. So that means we have here, if you look at the vector of the force field, it only has an x component, just like I drew here. So it always points toward y is equal to towards the y-axis. And as x becomes larger in its absolute value, also the field lines become larger. So this is what I depicted here in the graph. And now we want to specify some curve. That curve is denoted as curve C. And that curve is running from 0 to the point P. So 0, that is here. This is our first point. We call it also P1, and that is 0, 0. And the integral runs as specified here in the problem task. It runs to P, which is here x naught. So that is the curve here. This curve is what we want to integrate the force field over, 0 to P. And the x naught is, we denote this here as our point 2, that is given at x naught 0. So these are the two endpoints, the begin and the end point, P1 and P2, of our curve integral as specified for the problem of this example. And our first job is, as I pointed out, there are 3 steps. We first parameterize the curve, then we parameterize the vector field. Also, we had the step of parameterizing the curve. And now in the first example, you will say, okay, why to do all these cumbersome steps? And it is true, one can also do it simply by inspections, but let's do it the formal way right now, and then we'll see a further example, and there you will appreciate the advantage of doing it this way. So the first step is we parameterize our curve that runs from P1 to P2. And we denote our curve parameter as S. That means the general formulation is that we have a force of the parameter R, and we have a curve that runs along the parameter R. But we map that now to S, so that R will become a function of S. And our R of S is in our specific example given as S and 0. You see, because the curve is running only for from the point, basically the y parameter stays 0 all the time. Only the x parameter varies. So we have only S, and that is only along the unit vector in x direction. So S runs, it is an element, it runs from 0 to x naught. This is the parameterization of our curve. The second step is actually that we now parameterize the force field. It's step 2. We parameterize the force field. This far, we have denoted it as the vector f as a function of the vector r. And that shall be now mapped for the vector f as a function of r as a function of s. And the f of r, that, as we have given here, you see here, that is basically our constant times x. So we insert now for the force field for the vector r here the parameterized version of the curve. This is f naught times s times the unit vector in x direction. So remember ex, ey, and ez each is a unit vector of our coordinate system, Cartesian coordinate system. So in the third step, after we have first parameterized the curve, then we have parameterized the vector field accordingly. We have inserted the parameterization of the curve. And now we have to look what is the differential line element. So let's do this also. Let's adjust the line element. We have the line element. This is a general version d of r. And we want to have it as, this is basically a differential small line element. So we differentiate. Actually, I wanted to. So this line element is basically, we are taking the tangential component of that line element, and the tangential component is the derivative of that curve r of s with respect to s times ds. That will give us one. In our specific case, we see that the line is running only along x, so it will be only the x component along s. So that is now the third step. Now we have adjusted line element, and we can insert. We have to move this a bit down. So now we can combine all three of these things. We take 1, 2, and 3 and insert it into the integral. And this is the integral of w for our work. That is a line integral over the force field, so over f of r along r, and it follows the curve c. So what did we say? We said the curve c is actually runs from 0 to x naught. This is part of the parameterization of our curve. And the parameterization of our force field has yielded f naught, which is a constant, times s times the unit vector in x direction. You see, this is from step 2 here. This is from here. And from the third step, where we have identified the adjusted line element, which is just the x, the unit vector times the ds, that comes in here now. That dr turns into ex ds. And you see here you have these ex and ex. That is actually equal just to 1. You have here the unit vector dot unit vector. And for our integral along the work, it goes from 0 to x. Then that is minus f naught s times ds. So we integrate over s. Well, that will yield us, the minus is still there, and the other one will yield us a minus. Well, it will yield us a 1/2 f naught s squared. So this is just by integrating s. And yeah, the boundaries are 0 to x naught. And that is 1/2 minus here. Sorry. Okay, we can rewrite that also here. If you're looking here at that expression here, we can write it also in its components here, just what is written here above. We could, of course, have written it also in minus. This is the x component. There's nothing in the y component. Then here for the line element, we have 1, 0. times the line element. And then you see we have here basically dot product. So the whatever is here in that integral, we have the an integral for over to compute a work. So the work is not a vectorial quantity, it's a scalar quantity. So you can expect also that this integral will also yield you only a scalar quantity. Now you have here these two vectors, they connect via this dot product here, and then you obtain here. So whatever you prefer, you can write it here in the with the components only, that the selected components, or you write the whole vector here. As soon as you are account here for the dot product, then you are at 1/2. Okay, so short, you could have done it also just by inspection, and it seems to be a bit cumbersome right now to do that all the way with these 3 steps by well, you could have done it much shorter and just do it by inspection. You could have said that your work has to be integrated from along the integral c over f of r times dr, and that is obviously the curve runs from 0 to x naught. The force is just an x component, no y here, and the line element is 0 in y direction and 1 in x direction, and dx, that gives you the integral of 0 to x naught minus f0 times x times unit vector x times unit vector x times dx. So actually you see that was a lot of work now for something that seemed to be much easier if you do it by inspection, and that is true. But it's not so much true anymore if we look at the second example. So first example, you actually could have easily done also just by inspection. Okay, you have questions? Oh, sorry. I have to. I've changed the. I've started to write bigger and bigger. I will take care of that. Just a moment. I have expanded it so much that I can't shrink it right now. I'm sorry, but I'll fix this. Okay, I'll fix that later. Maybe I can scroll it now so that you can see all parts relevant. So the third step is, did you capture everything? Okay. Okay, I will zoom in here a bit because I start to um, zoom out, and then I inevitably start up writing in relation larger and larger. So, okay, that was the first problem. And you saw the concept, but maybe it didn't convince you so much because it seems to be more elaborate than necessary, because you saw you could do that by inspection much faster than uh, going here into this 3-step procedure by parametrizing the curve, then inserting the parametrized curve into the parametrized force field, and then adjust the line element. But these are these 3 steps. And now I want to show you this further example, and there I think this is more to be appreciated, that what for you do this. Okay, you see here now your x, this is your force field, F on R. And the force field this time has a x component, which is actually dependent on y and on x. And also your y component is dependent on x and y. So you can write this here in vectorial notation. You see here the x component is x squared plus y, the y component is x plus y. And now let's go through the same procedure as we did in the first example. Step 1, parameterize the curve. So first, of course, we have to see what are, or we haven't really set the curve. We have said that the curve is given by y is equal to x squared, but we haven't specified a beginning and an endpoint. So let's do that. Our beginning point is the origin, is 0, 0. And our second point, where they end the curve, that is 2.2 and 4. So now let's see how this looks, this curve. This is x and y graph. We have here 1, 2, 3, 4. Sorry? Oh, that I picked arbitrarily. So yeah, that is basically part of the problem given, but I just specified it now. It is not, you have to know. But the force field is given, and we have picked a line that we want to move along. And well, if we are at 2, then we will be here at 4. So we will go like that, the curve, roughly. But you have here only that is a starting point, P naught, and this is our end point. So here runs our curve, and this is our P1, and this is our P2. So parameterization of the curve, that means we want to have an S that enters here into our curve parameter so that we have an R of S. When you look at it, you see we can set S, we can map X on S. Say basically S is equivalent to X. Then what follows is that our Y would become a S square, and our S square actually corresponds to Y. So you see the disadvantage as far as we had actually an integration, but the field depends both on X and on Y, and we want to have one parameter. We want to have our curve parameterized so that we can operate with a single integration parameter. And that we can do now in this fashion here. And we say that R of S, the X component is S, the Y component is S squared. Or we write it in components, S times unit vector of EX and S squared times unit vector of EY. Starting point is R0. That's our point P1, and the coordinates are 0, 0. And the endpoint is R of S equal 2. That's our point P2. Coordinates are 2 and 4. So if you look at this curve and the definition, how this curve is defined, so y is equal to x squared, and if we look at the endpoint, that means for our parameterized curve, there's S runs from 0 to 2. This is the first step. That was a parameterization of the curve. In our second step, we do a parameterization of the force field. That means our F, which is a function of R, becomes now a function of R of S. Our F, compare it, we had said up there is x squared plus y in the x and x plus y for the y component of the force field. And we have, with the parameterization of the curve, have said that we use this mapping here. So this happens to the x, and for the y, we have to go in here. Let's do that. That means our parameterized force field, instead of being of x and y, it becomes now also formulated in terms of the line parameter. It becomes here, you see that x becomes an s, the y becomes s squared, and for the y component of the force field, we had x plus y. Again, the x becomes s squared. Sorry, it becomes s, like like in the first step too, and the y becomes a s squared. Yeah. So you see at the x component, it is actually 2 times s squared, and the y component is s plus s squared. And now you can write it and the x and y component separately. This is 2 times s square, the x component, plus s square ey component. Okay, so this is takes care of our second step, that is the parameterization of the force field. Now, third step is a parameterization or the adjustment of the line element, rather. The line element is the derivative of r of s with respect to s. That gives us the tangential component of the curve. Yeah. So for our specific example, we take, you see, we have our rs here. So we take the derivative with respect to s. S, first derivative of s is 1, and s square is giving us a 2s. So this is our adjusted line element. We have 1 times the unit vector in the x direction plus 2 times s the unit vector in y. Sorry? Hmm? Where? In the last line? Um, See, if you look, you mean here? This one? This one, yeah? Oh, that's a very sloppy X. Sorry. Yeah, thank you for correcting. This is EX. This one? Okay, thank you. Yeah. That was an extremely sloppy X. So to get to this line element here, to visualize that a bit, you have here some arbitrary curve. Yeah, this is our curve. And at any point, you can look, you can specify here a tangential vector here. And you multiply that here with the line element. So the idea is you segment your path so into small differential elements. You have your path that has a varying r along that curve, and you segment that into small r elements. But each of these elements basically consists of kind of the tangential component of that of the vector r at that position, and this unit element along for the slope. So you follow this curve and you take divide it into small segments and take the tangential element to this curve in each of these segments. So now we have taken our 3 steps. And well, now we can take these all together and we insert them into the force integral. Insert 1, 2, 3, just like we did in the previous step, but now I think it's a bit more interesting. In the previous one, you might have said, why so much trouble for something which you see right away how to do? Here it actually pays off. So we have our work W here now. We integrate along the curve. That means we go from S1 to S2. We have our force, which depends on R, which depends on S. We have taken our line element. So this basically is our tangential vector. And that runs now from 0 to 2 in our specific example. Well, it's a specific example now. The force we said, if we express it in terms of the parameterized curve parameter, then you see it's 2, yeah, it's 2 s square and s plus s square. That's our force. Then our line parameter is 1, and the y component is 2 times s. So what comes in here? If I take the inner product here of these 2 vectors, what do you find here? Okay, it's 2s square times 1 plus s square times 2s gives you 2s square plus 2s to the power of 3. So we integrate from 0 to 2. Okay, we have 2s squared plus 2s squared gives us a 4s squared. And then we have the 2 times s to the power of 3. We integrate that. And so what gives us the integration of s squared? Gives us s to the power of 3 over 3. We keep the factor of 4 in there. What gives us the integration over s to the power of 3? That gives us s to the power of 4 over 4, and we keep our factor 2 in there. Integration boundaries are from 0 to 2. So we insert 2 to the power of 3 times 4 third plus 2 fourths times s to the power of 4. So this gives us 32 third plus 8. And the other one, the other boundary is 0. That doesn't give us any contribution. Alternative way to write it down, you could say, instead of writing it into the as a vector in a bracket, you write here 2 times. So if you are here at that point, you take this here take the individual components and give them along with their unit vectors. That would be for your force field. And then you take here the inner product and you give here your parameterized line element. You see that it's just a slightly different notation, but gives you exactly the same. And you can do it whatever whatever you feel like. So we sum up the components again and so on. Okay, this basically was a little bit a recap of how you go about doing your line integrations. And the use case for that, I mean, this was also kind of an example, but it was a quite unspecific use field with a kind of generic force field. And we can go now and see how we deal with it when we are actually having some problem with some actual electric work. How do you keep it, by the way, with breaks? Do you like to have a short break or, yeah? Should we make how many minutes? 10 minutes? Okay. Oh, well, maybe 10 because I have not so long today anymore, but we can next time have a bit longer also. Okay, then let's have a 10 minutes break.
For the okay, so for our content assessment, right? So when will be our will there be quizzes or will it based on attendance or whatsoever or
Yeah, there will be also quizzes. I will announce it. I think for beginning of next week we'll have one, and then there should be also a second one. So there will be a couple of quizzes.
so so are they both on Mondays?
Hmm?
Are they both on Mondays? Are both quizzes on Mondays or
I have to check with Ms. Fong also, but I think Monday or Tuesday.
then any cheat sheet, any formulary that we can use? Like what are the guidelines?
For the quiz,
Yeah.
now so that would be closed book, no cheat sheet for the quiz, and there will be for the exam there will be some formulation that I will distribute, and I will put that online also. I will, but this is a good point. I will also just announce it then what how the how that will be handled. So it will be closed book exam also, and also for the quizzes. But for the exam, there will be some formula sheet that will be distributed.
So the quizzes are 10% each.
So the quiz will add up to 20%. Yeah, yeah. This is because if you look here, no? Here, yeah, here you have it. So you take the derivative of r with respect to s. You differentiate.
Oh yeah, because differentiation means a tangent, right? Differentiate something you get the
Yeah, if you differentiate along the along s with respect to s, you get the tangent. So yeah.
So the bar is then the below. Yes, the
Like, where do you get this?
See, you have here.
Oh, wait. Oh, no. Oh, yeah. You just multiply it.
You multiply here. You have s square times 1 gives you this one.
x times ex becomes
Yeah,
1.
yeah,
Then
yeah.
yeah,
Okay.
and here this one here becomes s times 2s and s squared times 2. So yeah, this there you have to be careful because you have the inner product only that ex with the ex and the ey with the ey, but then you lose here basically the this becomes scalar now. Before you have here the components of the
This one
vector
don't multiply.
because you take the inner product. So this does not x and y do not yield a contribution.
Thank you.
How do you get this? Well, S is an element of 0, 2. Like,
Yeah. So this is basically a bit on the decision to have that running from P1 0 0 to P2 2, which is 2 4.
right.
And so that means for x, if you look at the x component, which translates into s here,
Right.
that runs from 0 to 2. But the end of and the beginning is in the end now arbitrarily chosen for the sake of the example.
Right.
Could be also different.
So basically, this 0, 2 is you're referring to the x to the x coordinates, right?
Uh,
S0 and S.
Because it, it happens to be like that because I have mapped the x to the s,
Right.
and so the endpoint for s and the beginning turns out to be then 0 and 2. Yeah. So the parameterization is basically that I use as a line parameter s,
Right.
and it runs from x. It runs from 0 to 2 also. Yeah.
Let me digest.
Okay. Well. Yeah. Sure. Yeah.
Yes, but I think someone.
Oops. So. I'm just. Probably switch it on and off.
No.
Yeah. I want to familiar with that. I'll try later on. I have to, but I think I don't need it in the break.
Just telling me the direction of this
Sorry?
force. This
Sorry?
F naught is
Yeah.
just telling me the direction of the force. So if my x is negative, I bring this way, this whole thing will become positive.
Yeah.
So it's telling me the arrows of
Yeah. The arrows are the arrow direction is changing as you move into negative x.
Yeah, that's
Oh, okay.
it's so the F is the center of the attraction. Basically, like the lines converge. So F is the center.
Oh, okay. Thank you. Okay, thank you. Can
Welcome.
you increase your mic a bit?
Yes, I just. Okay, so welcome back. Okay, one thing is I have your attendance sheet has come back to me again. Has everybody entered? Don't forget to sign up. Then also there was a question about quizzes. So I don't have the specific date, but probably the week to come, Monday or Tuesday, I will talk also with the administration. And there should be a couple of quizzes, and they will make up for 20%. And quizzes will be closed book. Also, the exam will be closed book for the exam. However, I will give out some formula sheet. Then also I will upload it up front so that it will be the formula sheet that you can use for the exam. There's no sheet for the quizzes. And yeah, any questions, then just bring it up. I hope, yeah. Everything that's in the lecture. But the quizzes will be, I don't want to say it will be exclusively multiple choice, but there will be a lot of multiple choice questions. The final exam will be actually where you have to do problems like we will do in the tutorial. So qualitatively, they are different. The quizzes shall be probably, yeah, it will be, I would say, easier than or no, I mean, in the sense, if you have multiple choice, it's usually uh, a bit easier then. But so for the exam, be prepared to do more problems like we do in the tutorial. And for the quizzes, these problems, there will be a lot of multiple choice and there will be smaller things, but they will not have too much detailed calculations or so, things like that. Yes, there will be problems to practice on, also past exam problems that I will put on. So be prepared. The quizzes will be different in format than from the exam. So you will see some past exam quiz will be different. It will be also many multiple choice questions, but not exclusively multiple choice. So I'm trying to speak a bit louder now. I hope you can understand me better because I heard it was not so good in the beginning. Now we want to look at electric work and electric voltage. So the whole thing that we have done this far with the math recap is basically serving that we can do our calculations of electric work. So here I have here the next gap text. The electric field, as we have seen, is a force field. And what happens, you have a charge. We have seen the electric field basically gives you a measure for what kind of force any charge that you bring into the electric field will experience. And then if you take this charge and drag it through the force field along some trajectory, you obviously have to put in some work because you have to overcome a force. Well, it depends actually if you have to overcome some force, because there are potentially also options where you can move the electric charge in the force field without actually having to exert any force. But as soon as you have to exert force, then you have to contribute. I mean, you have to bring in the work. So you have an electric field is a force field, and if you move some charged particles in electric field, you have to perform mechanical work. So the simple case is that the force is not depending on location. Basically, you have a constant force field. And simple case also is if you have a straight line. And let me show what that could be. We have to bring in mechanical work and, okay, it's working again. You have to bring in some mechanical work. And the simplest case is basically think of having here. So this is a general that could be also, this is some body here or some charge. And you want to move it along this path here. You want to move it by delta R here. And now we have the situation that the force field is pointed or is aligned here with this direction of your motion, that where you want to move it in, and also that F is constant. So you have no variation of F. It remains constant over the entire space here, meaning F is not a function which has an R dependence. Yeah. Then this is the first case. The mechanical work that you have to put in is given by the force times the delta R. And in this convenient case, because F is constant, it is not a function of R. You can just take the absolute value of F, and for the reason because it's constant and it is completely aligned with your delta R. Yeah. So that means you basically just have to take the absolute value of the force times the absolute value of the distance you're shifting it. But things might get a bit different when you have a force which is, for example, directed. Okay. If you have forces and now not aligned anymore with the direction of your motion, where you drag this body through the force field, you could have something like this. This is now the second case, and I draw it in red. Then you have a component of the force vector. You can split it, you can decompose it in two components. You can split it in one component that aligns with your path element, with your delta r. And the other component is basically the rest of the force vector. And you say you have an angle alpha in here. So that is the second scenario where you bring up a mechanical work, and again you have to take the inner product of the force vector times the delta r, you see. But now this is not just the product of the magnitudes of each of the two of the force and the r vector, but you have to basically see that you are only taking that component of the force vector which aligns here with the path where you drag that body or the charge, whatever you have here, only that component that aligns with that path vector or the r vector along the path integral, only that is contributing. And that means you have here f times delta r, also absolute, but you adjust it by the cosine of alpha. So you could also say that only the force component parallel here, I do it with these parallel dashes here, parallel to the path where you move the body here, only that is contributing here to the work. So now you can also think of a more general case, that is case C, and you have here some arbitrary curve integral, and you have your body there, your object or charge or whatever that needs to be, which is experiences a force, and you want to drag that along that path. So here is your delta r. But now you have this special case where you have here at that part of the path a force acting in this direction, position r1. If you go further in the path, position r2, you might have different direction and also possibly a different magnitude of the force. You have a force vector of r2. That means now you have also a dependence of f that is changing along the path. So this is more or most general case. So the work only, with respect to the work, only the components of the force vector which are parallel to the curve contribute to the mechanical work that you have to do. And depending how complicated your problem is, you have to account for a change of the force field along the path with respect to magnitude and direction also. And in any case, you have to basically project your force vector always on the tangent of the curve that you integrate over to obtain the right contribution for the mechanical work that you have to exert. So the work only components of the force vector parallel to the curve contribute to the mechanical work. That is important to consider. And that you also saw in the previous example for the math recap. We had in the first example a force field which was only directed in x, and we had also a curve integral which was only which was parallel to the x direction. So that made it not necessarily to do any projection also on that. That made the integration also very simple. So yeah, that is actually the first force vector here is slightly upward. So it is not aligned with the direction of the curve. So you have to do a projection of that force vector at the first location to see which component of this force vector is parallel to the curve element, to the delta r, and only that component you take into account when you integrate. And also you see at the second position the direction is also again both of the force but also the tangential component of the curve, both are changing. So at every instant you have to see how has the force changed, how has the curve parameter changed, and you have to project it always on the tangential component of the curve. And then, yeah, then you integrate over it. So the general case is the magnitude and directions of the force depend on the location. So this is what I've sketched up here. That means the force field is not constant. And if you move something along an arbitrary path or curve, then you have to take that into consideration. And here comes in what we have done in just now in this math recap. You have now a curve C, and it runs from point 1 to point 2. And in general, your curve element, delta r, is not parallel to f. That is a general case. Second, the force field is position dependent. Also, that is a general case. Force field is a function of r, and it's not constant. And what you do is now you do a piecewise summation along the curve. And let me plot you for that for you. You have some curve that runs from P1 to P2. And at every point here, you have here your first element, delta R1. Then you get your second element, delta R2, delta R3, and infinitely many. No, not infinitely, but depending on how in the end you transition into infinitely many. So your tangent here is changing, and also you have here a force vector, and also that can be different here. So this is r sub n, and then each time you have to see what is a parallel component here of the force vector to r. So this is f parallel for r sub n. So you have this curve and you divide it into a large number of small segments of this curve, and you look for each segment what force is okay, you have to specify, of course, a specific point of that segment, maybe the beginning segment, but in the end, you make so many segments that this becomes an ever increasing better match, and basically you transition to a integration of infinitely small segments of the curve elements, and for each segment you project your force component of the force field so that you get only the parallel component that is parallel to that line segment, and you add those parallel components up. So basically you do this piecewise summation along that curve C, and each piece, or sorry, each, if you take these small segments, you also get for each segment a small delta contribution to the work that you're bringing up or putting in here. And that is the force at the segment R sub I times the length here of that segment element R sub I. And that is basically the absolute value of R sub I. Oops, sorry, the screen has vanished. And now it should be back. Okay. And times here the cosine, cosine for the respective angle here for f sub I. So, or you can also say it's a parallel component of the force vector times the segment. Okay, and now you calculate the work. Basically, you calculate the line integral in the vector field along the curve C, and the total work performed along the path C is then obtained by basically summing up all of these delta omega, delta wi sub I. So these are the infinitesimal contributions to the work along these segments of the line, and so those you add all up. So then you add the total work. The total work performed along path C is obtained by summing up all delta W sub I. So that basically means you have, so what do you do now to get an accurate result? All delta W sub I. So you see here on that curve, each element here is a delta R sub I, and you obtain the force at this position. And you basically have segmented your curve into small delta Ri, and you make them increasingly smaller, and each gives you a contribution, and then you sum it all up. Now, the advantage is the smaller you get those, the more accurate you become with your integration, because in the end, first it's a summation, and you make these delta smaller. So in the end, you integrate and you become more accurate in this. So that's what we need to do. We need to get an accurate result. In order to get an accurate result, we have to make first delta R very small, so that we go from our delta to this, basically that we go from transition from adding up small elements to go to an integration, making our delta infinitesimal small. And this means we replace the sum by an integral, and that means our work becomes integration over f of r over r. And the integration follows the curve P from P1 to P2. This is our general. So if you look at it we graph that here, we run from P1 to P2. We have here our delta R, and you may have some arbitrary force field here. So this, I draw that in green here. This is your force field, and you pick along this, through this force field, you place in this integration path, and as you do that, for each point here, you project, you look what the tangential component is, and you also search for the tangential component of your force field here at each segment. So in the end, you have a curve or respectively path integral in a vector field. So now something to solve. This was a general formulation because you see there was just a force field. Now, how does it look for the electrostatics? Well, our force is the charge times the electric field. And we have seen if we have a line or curve or path integral in a vector field, then we have to follow 3 steps. We have to basically follow 3 steps, and these I will list here. This is basically what we have seen just before the break when we were looking at or a little bit earlier today, when we were looking at the math recap. Then we named 3 steps. And the step 1 was to find the parametrization of the curve of C of P1 to P2. We have to find the limits of the integral, which is then fitting the parametrization, because as we parameterize it, of course, the limits have to be adjusted too. That was the first step. The second one is let's parameterize the field also accordingly. What does it mean? Basically, that means let's insert the parameterization. And the third part, you remember, is adjust the vectorial line element. This dr we have to adjust to the parameterization also. And how do we have to do it? Well, we have to do it in a way that we also follow the curve then. So keep in mind, we want to solve our omega, which is the curve integral from P1 to P2. We have our line integral here. It goes from P1 to P2. And we look for the tangential component. He is a tangent. Then this becomes here our S. And we have a total length L. Recall we did first introduce a parameter S that is following the curve. And we specify the limits. So we have to give the limits. It runs from 0 to L. And then we have an S that we insert into our, basically make our curve that follows R. We make that as a function of S. And then with that, based on that, we have the second step, parameterize the force field. That implies that our F of R is going to be F of R of S. And I think earlier we have seen also that benefit in the recap of doing this. Nah. So, and now we adjust the line element and the integration limits. Okay, so what does that mean for the integration limits? Or no, let's rather say what does it mean for the tangential component? Well, our curve is now represented by a sequence of tangent vectors, and each of these tangent vectors we obtain by taking the derivative of r with respect to the line parameter s. Then this gives us that tangential components. So recap that here. I think this is quite an important aspect. So our curve can be represented by this sequence of tangent vectors, and these tangent vectors are basically then t is dr of s with respect derivative with respect to ds. So then you see when you look at that, then the line element that you have to include at the integration becomes just t times delta s. And the nice thing now is that if we are looking at the mechanical work along any arbitrary curve, then the formulation transitions in the following way. So we assume that we have this position-dependent force field. So in the formulation we have just seen, we have come to the point where we now first have taken these small segments of delta r that we have made smaller and smaller till we ended up at the concept of integrating these along that curve. This is what we just had figured out is the correct way. And now we merge that with the parametrization that we have seen earlier in the math recap. And that means we make our curve a function of r of s. We run from 0 to the point S1 here to S2, which is L, integrate over F. So we have our parameterized force field, and the adjusted line element becomes, well, basically we have to take the tangential component, and this is also equivalent here to taking the force field of R of S here. Okay, so this is our equation 1.6, and this is also something to be highlighted. Okay, so the electric work then in the end is F of Q. Sorry, to get to the electric work, we take F of Q, that is the charge times the electric field, and then we integrate that over the distance where we move the charge. So that means the work is Q times the integral over E, and that is our equation 1.7. Okay, so I think now it would be nice to see more specific use cases again. And for that, we look at the example for a point charge. So we know the force is given by the electric field and the charge. And if we drag the charge along that path, then we integrate and we find the total work here in this formula in equation 1.7. Now, we have to see what happens with a point charge and what paths actually may contribute to the work that we have to put in, and maybe other paths are not affected here. So let me get, okay. Let's have our charge Q here. And we know that the force field goes here in all directions. We have a single charge. And this charge Q with the capital Q, that is basically now our generator of the electric field. So we have a large charge in the center, or a single charge actually also that defines also our center. And now the question is, what happens if we take a small sample charge and move it around? We have seen earlier already on the slides what forces to seen qualitatively, and now we want to bring that in the aspect of what happens when we are actually moving it. How does that affects how does it affect the workforce? What work do we have to contribute to that? So in the center we have the point charge Q. That is our generator of the electric field, and then we take a small test charge Q that we could place, for example, here. This is our test charge Q, and you see the main charge here in the center is contributor to the electric field, or to the force lines that you see here plotted in red. And in terms of our location of the Q test charge Q, that is given here with the unit vector ER, which is a radial vector, and we have that positioned at R1. Yeah, this is at R1. And what happens if we want to bring it to R2? This is our radius R2, point charge Q. So important because it's a point charge. We have a radial symmetry. What is actually right now we're looking at only at the two-dimensional case. We have here x and y basically, but of course if we are now this is all radial, If you are looking at in a three-dimensional case, of course, then we have here not a radial but a spherical symmetry. Where is the Q? The Q is located in the origin of the coordinate system. And then I plotted in the small q, the test charge q, that is moved then from radius r to radius r2. And you see also again here the test charge does not contribute here any to the field lines. This is justified basically by saying that is a very minor charge. If you want to make it very accurate, of course, you would argue that the test charge